welcome to Module 17 on Optimization Basics, Gradient Descent and Variance. So at the end of this module, you should be able to explain the role of optimization in the machine learning pipeline and its relationship to empirical risk minimization, which is the concept that we introduced way at the beginning of this course in previous modules. You'll be able to derive and implement basic gradient descent for simple regression objectives. You'll be able to distinguish and compare batch gradient descent, stochastic gradient descent, and mini-batch stochastic gradient descent in terms of speed and noise. You'll be able to tune and diagnose learning rate and batch size using loss curves and simple metrics, and describe the intuition behind momentum and adaptive methods like ATOM. A lot of these terms we haven't defined yet, and we're going to define them for the first time in today's module. And I should warn you that each of these topics can be dealt with in a ton of depth. This being an introductory course to machine learning with a lot of other topics, we're generally going to scratch the surface a little bit here, but there's going to be citations throughout that I highly recommend you check out to go deeper, because it's always a good idea to learn more. Let's scaffold our concepts again. So where does optimization fit in the idea of machine learning? And maybe have we been doing this already anyways, or is there something more to it? So we talked about the supervised learning pipeline, in which we first chose a model family, or say an architecture. This could be something like we're going to choose to use logistic regression, for example. So the form of the function f of x with the parameters w is our model family, and we can choose it. This is our hypothesis space. We're going to choose a loss. Sometimes this loss was kind of like obvious to us. If you're going to use, if you're doing regression and you're trying to predict a continuous value, you're just going to use a mean squared error. But maybe you're also going to have a regularizer, like we talked about in the previous module. And you'd add that regularizer with a term, with a weighting term, to come up with your overall objective that you're trying to use for training. Then you want to optimize the empirical risk, maybe plus the penalty, hopefully plus the penalty, to find good parameters W that work well on the training data and also generalize well to held out data, or should generalize well to held out data. And then you're going to evaluate and deploy. So this is nothing really new to us. The optimization part is step 3. We've already kind of been doing optimization already anyway. What we want is some ideal set of parameters, W star, which their values give us the minimum overall computational value of the objective function j. And j, so far, up to now, is now going to be a combination of the empirical risk r hat, which could be like the training loss, plus the regularization loss or term, which is weighted by lambda, which we talked about in the previous module. So for some models, so some model families, this overall solution will be a closed form. There's literally an equation that we can just type everything into, and we can get the best possible values for W with no ambiguity, as long as we're given the data and so on. So ordinary least squares is an example of when a closed form solution might exist to find an ideal setting W star. But for many others, logistic regression, neural networks, the more complex regularizers we only hinted at in the last module, there's any kind of iterative procedure will require iterative optimization algorithms in order to generally get better and better weights, starting from some potentially random weights and getting better weights that better and better represent our data and generalize well and have all these other nice characteristics. So there are some trade-offs in optimization we've already seen. There is accuracy versus compute. This is sometimes a little bit more of an engineering problem, but if you mean to deploy your model in real life, you care about how much it's going to cost you, how much energy and power you're going to use, how big of a model you're going to have to fit into memory. So generally bigger models might be more accurate in general, as long as they've been regularized effectively, but that means they're more expensive. There's this global view of the loss surface versus local, potentially noisy updates. There's an overall loss surface, only a small part of it we can actually see. And as we traverse over this surface, it's kind of like walking blind through a region for which there's no map yet, and we have to kind of map things out as we go. Some models have theoretical guarantees, like their performance will always be better than this. But then there's also practical performance on finite data. So the theory can tell you you'll always be better than this, but how much of that range is actually going to be explorable in practice is something you have to also consider. So you need to balance theory with practice. Gradient-based methods, and we've already seen gradient-based methods before, are kind of a sweet spot. They're going to use the local slope of the loss surface, which we saw earlier. We saw a bowl, and we want to kind of move downwards through the bowl by following the gradient, by following the differentials or the partial differentials as we move downhill, and we minimize as much as possible the objective function until we're left with something satisfying. And this can scale well. Gradient-based methods scale well to large data sets with high dimensions, and in particular, stochastic gradient descent will help solve this problem for us. So here's a one-dimensional intuition. Again, we're just scaffolding our conceptions at the moment. Consider a smooth function j. This is our objective function we're trying to optimize. And we have a single parameter w. The gradient, or the partial derivative, we can call j prime of w. This will tell us, the sign will tell us which direction increases or decreases the function. So if we have a particular setting of w and we want the overall surface, the function itself, the thing we're trying to minimize, the objective function, we know which way is down because we have the sign. The magnitude will tell us how steep the slope is. So we want, if we're at a point and we have multiple directions in which we can go down, we kind of want to go down in the direction which is maximally negative, which has the steepest slope. So the gradient-based descent update in one dimension, we'll start off with some parameter w sub t. This is what we have at iteration t. We will compute the derivative for that particular value of w at the particular iteration t. We can weight it by this thing called eta, which I'll define in a moment. This will define how we want to change the weights. So we take our original weights, we subtract the amount we want to change, and then this will give us a new weight w at iteration t plus 1. So we started off with one parameter, we computed the gradient, we jumped to another value of w at time t plus 1, we compute the gradient, we jump ahead, we have a new setting at iteration time t plus 2, and so on. We have this setting eta, this n-looking thing over here is called eta. This is the learning rate. It's bigger than 0. This can be seen as the step size, and it's one of those hyperparameters that we might want to optimize following a procedure that we talked about in a previous module. If the derivative at a particular point or a particular setting of your parameters is greater than 0, that means that the function is increasing, and that means you want to kind of move to the left. You want to decrease w. If the differential is less than 0, that means the function is decreasing, and you want to move towards the right. You want to go down that hill and go towards the right. And the larger the absolute value is of this differential, the larger your step's going to be, and it's going to be scaled by eta. Here's a little visual of it. At iteration t, we have a particular setting of w. It's almost exactly -1. So this is could be our coefficient for a regression curve or something like that. The blue is our objective function j. This is the overall thing we're trying to optimize. This can be a combination of the training loss, the expected empirical loss, plus the regularized loss, like a lasso or a ridge loss, or the elastic net loss. Whatever it is, it's going to be a curve shaped here as this blue curve. And we want to minimize it. We want to go down as quickly as possible. So here we are at this red point. This is our current setting for our coefficient, our parameter. We can compute the derivative, which essentially is the tangent line over here, this red dashed line over here. This is highly negative, so the slope is pointing downwards. We want to jump to the right. How much do we jump to the right? Well, we scale this derivative by eta, and this will tell us how much to change the value of w in the positive direction. And down here, we jump to our new setting of w. So at iteration w sub t plus 1, now the value of w is just slightly less than 1. And our overall risk plus the regularization, our overall objective is lower. So we're making improvements on our training data. Again, we want to minimize our objective function here. This generalizes to multiple dimensions. So usually we don't have this one number that we're trying to optimize, but we have a set of numbers. The set of numbers can be represented as a vector, W. This is a d-dimensional vector. So each of the weights will be a real valued number, and we'll have d of them. The same concept applies, instead of saying j prime or j apostrophe, meaning the derivative at that particular point, we'll zoom out of my face, thus, and continue talking. We have an overall objective function j, which will be a function of multiple variables. It'll be, the first weight, the second, third, fourth, all the way down to the dth. And if we take the derivative in each of those directions, we'll get slightly different values. Like at a particular point, the objective function j might be decreasing in one dimension, but increasing in the other. So we want to compute the derivatives in each of our dimensions that we can change, which is our d dimensions. So this nabla, this upside down triangle, is just the gradient vector. This is just a vector of length d, which consists of all of our partial derivatives of the objective function, j with respect to the first, j with respect to the second, all the way up to j with respect to the dth. So this is a vector of partial derivatives, one for each parameter. And now our weight update. Remember, our weight w is a vector. And then for each element of that vector, for every weight, for every parameter, we can just adjust them basically the same as we've done before. We'll have a scaling factor eta, which is our learning rate. We'll have a vector of partial derivatives, one for each parameter. And we'll just subtract the second term from the first on a case-by-case basis. So, w sub 1, we subtract n times the partial derivative of j with regards to w sub 1. W sub 2 will subtract eta times the derivative of j with respect to w sub 2, and so on, all the way down to d. So we'll end up, this subtraction will give us a vector. This will give us a new setting for each of our d parameters, which will be our setting for weight at iteration t plus 1. Okay, so we're still learning in an iterative fashion. Now instead of having one weight we're updating, we have d of them, but we can update all of them at once, and we can kind of keep on trying to follow this curve downwards to minimize the overall objective function j. Okay, and every time we do this, hopefully we'll get into a lower point and we're getting better and better results. So each iteration so far is going to use the full training set to compute the gradient. So just like we saw before, the empirical loss will be like a sum over every element, every data point in our entire training set. So the first term of our objective function will be computed over all of our training data. But this can be expensive, especially if we have massive, huge data sets. And sometimes we may not necessarily need all of the data, but just using a small sample of all of our training data will still give us the right direction to move in as we're updating our parameters. And if we sample in a careful, smart way, we will have still stable directions, and we can still do the same kind of learning, but without having to use all of the training data within our objective function j. So the intuition here with regards to convergence, we're trying to converge on an optimum point. For a simple convex smooth function, so we have the bowl shape and it's smooth all the way down, gradient descent with a small enough learning rate will decrease the objective almost every step. So every time we go from time or iteration t to iteration t plus 1, the objective will get smaller and smaller. And we'll converge to a minimum. Hopefully this minimum is the best possible minimum and it's globally minimum. So for this course, you'll want to remember this, and hopefully you're going to see us through experimentation, through our workbooks and everything. If you have too large an eta, and you're taking big, huge jumps at every iteration, then this is going to result in instability or divergence. So you're computing your derivatives, but then eta is so big that you're jumping to a very distant part of the bowl or of the objective surface. If you're jumping around wildly or taking too big steps, you're going to diverge, or things will be unstable and you won't learn anything very effectively. And this is something you observe through experience. If eta is super, super small and you've taken very, very tiny steps down this surface, it's going to take forever to learn anything meaningful and to go down this well into an optimum, minimum area. So you want to tune eta empirically using simple losses and using iterations and so on. We'll talk about this soon enough. Here's a work derivation. This is gradient descent on a one-dimensional quadratic. So this is a function in which our objective function now is just going to be 1/2 of a times w squared. So this is a quadratic because we're dealing with a function where our variable is to the power of 2. A is bigger than 0. This is a constant that basically just controls the curvature of the function. The gradient with regards to omega. So you take this function j, what is the derivative of j with respect to w? Well, this 2 comes down over here, the 2 on top, cancels out the 2 on the bottom, this becomes 1, and all we're left with is a times w. So the derivative of j with respect to w is just a times w. Okay, so this is our derivative. We can plug this derivative into our update function from a few slides ago, which we do down here. We have our original value of weight w at iteration t. We subtract the learning rate times the derivative, which is just a times w at time t. You can move things around a little bit if you want. So it's just 1 minus n times a times w sub t. If you only have eta computed once and a is a constant, then this computation can be done fairly quickly. This subtraction you only have to do once. Store it somewhere. Anyway. And then you iterate. So if you iterate in this way and keep on updating, because this function is so simple, this is really a corner case. It's really kind of pathological. It's not like the kind of data or objective function you're going to see in real life, but just to hammer home the point. This function applied over and over again, t times will, because this is a constant and you're multiplying this constant over and over again, this will devolve into 1 minus eta a to the power of t times whatever the original setting was for weighting at the first iteration at time 0, iteration 0. And the convergence is described thus. If you need, or we need, the absolute value of 1 minus eta times a to be less than 1, the absolute value has to be less than 1 if we want w sub t to converge to 0. That is to say, if 1 minus eta times a is between minus 1 and 1, this results in, this is exactly eta times a being between 0 and 2, or eta being between 0 and 2 over a. This is really, again, really pathological. I'm just I should have the magnifying glass here, or the microscope, because this is a little bit of a diversion. So if you're tuning out now, it's perfectly fine. We're not going to see this exact derivation again, because this objective function is so simple. But the main takeaway I'm trying to get across here is that there usually is a range of stable learning rates. Here it goes between 0 and 2 divided by a. But within this range, eta being smaller, it might be safer, but it's going to be slower. And even if that's true, even in this very pathological, super simple case. So this is proven. Normally when we have objective functions that are dependent on data, you can't have this kind of closed form solution. But empirically, this overall takeaway, or the set of overall takeaways, will be true from this pathologically simple case all the way up to the most complicated transformer neural networks. A lot of machine learning losses can be considered as generalized quadratics near some kind of optimum, so that the same intuition applies. So the reason why real performance will have these same kind of takeaways as this super simple fictional case is indeed because machine learning losses can often be seen as somewhat being generalized quadratic. So that's an oversimplification. So we kind of hinted at the reason that, at the concept that using all of the data for training might be overkill. And what we'd like to do instead is to sample the data carefully so that we can do training just as effectively, but with a lot less data. Effective, but efficient. So for an average loss over data, we saw this over here. This is like, we're not regularizing anything. We have some loss term and we're using all of our data n. Batch gradient descent will use this full entire sum every single step. In stochastic gradient descent, at every step t, or iteration t, we can randomly pick some index or some collection of indices in your training data. Call this I sub t. This can be different at every step t, and update this way. So as you can see here, our update function takes the same form as before. We're still taking the weights at iteration t and subtracting the learning rate times the gradient of our loss function. And we might have a lot of different weights we're dealing with, so w can be a vector. But now we're, instead of taking the loss over all of our n data points, we're going to just take some subset of data points described as an index vector I sub t. Okay? If you're being super cheap and using index is literally one value, so you're taking all of our n data points, choosing one of them, computing the loss on that data point. So it could be a classification loss, and you're doing classification, and that's your loss, or you could be doing regression, and it's just the difference between the prediction and the true value, or the observed y. This is going to be very cheap. You don't have to sum over anything, so it's very expensive. Updates are going to be noisy though. So every time you iterate, every time you go from one weight setting to the next, it'll be noisy because you're only taking one sample at a time, and all of the noise that we talked about before in the bias and variance and inherent noise, you're going to have a bad time because you don't know how much bias or variance or noise you have for a particular data point, like general noise for a particular data point. So you're going to explore this loss surface, in a very noisy way, but potentially, over the long term, maybe this will balance out. In general, this can generalize okay, especially in deep learning, but it's going to be advisable not to use like one single example at a time. Rather, we like using mini-batch stochastic gradient descent. In small batch mini-batch stochastic gradient descent, you'll take just 32 or 128 examples. So this is kind of what I was alluding to a moment ago. Now our batch will look like this. Here, before, when we were summing over all of our n data points in our training data set, we still computed our loss. Now we're just going to sum over a subset. So we're going to sample some batch b sub t. Often this is something like 32 or 128 samples, and often this comes randomly. So we randomly choose 32 or 128 indices from all of our training data. We pull those out. That's our small batch at iteration b sub t, at iteration t. We'll compute the gradients for all of those. We'll sum over those gradients. We'll normalize by the number of elements we have in our small batch, for example, 32 or 128. This is essentially the average gradient over each of the stochastic gradient descent samples. So again, it takes the form of an average. It's a sum over all of the gradients divided by the total number of examples we're dealing with. And then, given that average over the stochastic gradient descent for each of our elements, we'll have our good old-fashioned update function, which is our old weight parameters minus eta times our gradient, which in this case is the average change in gradient over all of our b sub t sampled examples. So if this batch size is 1, if we only have like a setting, the batch size is exactly 1, we have good old-fashioned stochastic gradient descent. We have one single index now, and we're just doing SGD. If the batch size is n, then we're doing the entire data set, and essentially this devolves into full batch GD, so we're not really gaining anything. But in practice, we're trying to have a bit of a balance. We're trying to get a little bit of the benefits of taking a large amount of data at a time, which can be more universal, but it lacks the kind of noise we like. We can take batch size 1, which is extremely noisy. but it's very cheap, and some balance between these two things would be random samples of batches, and that's our B sub t. A couple of variants before we get into examples. There's this idea of momentum. Momentum, the idea is that we have a running velocity, like an overall speed that we're running down this hill, and it'll point in the direction where past gradients have consistently pushed us. So here we have yet another parameter, beta. So now our new vector v at iteration t plus 1 is going to be a combination of the vector v sub t at iteration t times our new hyperparameter beta plus the differentials of our objective function related to our weights at iteration t. And then we'll update our weights. Our updated weights will be the weights, whatever they were before, minus eta times v, this whole new function over here. So all we're doing right now is adding a term to our differentials, which is this beta sub v, beta times v, which basically just describes the overall velocity we have in any particular direction. So v is so named because it's a velocity, and it basically says how much we're moving in a particular direction down our empirical risk surface that we're trying to minimize. Eta is still the old learning rate. Beta is going to fall between 0 and 1. Normally it's not going to be exactly 1, but this is what we call our momentum parameter. We're going to see an example of it in a second, I hope. The intuition is basically, if we have narrow valleys, if your objective function isn't like a nice smooth bowl, but will have a lot of very spiky valleys that are very small, if you just kind of follow the surface all the way down, then you're going to end up potentially in a hole. And doing old-fashioned gradient descent can potentially zigzag in a way that we don't like. Momentum will accumulate these gradient directions that are consistent, and if the updates are consistently in a particular direction, this path will be smooth, this zigzagging behavior will be minimized, and will often converge faster. And there's some old papers on how to do this, going back to the 60s, and the idea from physics about the momentum of heavy balls rolling down surfaces. But then this was updated in the 80s in machine learning, and relatively recently in 2013 on momentum in deep learning. So the papers will be provided to you. So we're going to exemplify this on this simple bowl here. This is a top-down view of our surface that we're trying to minimize. So this is just a topological map, and we want to get down somewhere near the bottom. And you can change this step. So here I'm taking steps. I'm going from step 5 now to step 6. And as you can see, here we have a gradient descent in red, which is taking its sweet time to get close to an optimum. And momentum, in this case, is, it's a different example than the one I mentioned earlier. This isn't the situation where you have these very narrow valleys. So the zigzag performance I mentioned earlier is going to not be the case here, where we have a single smooth bowl. It looks like the momentum-based approach is zigzagging a little bit, but effectively what we're doing is realizing that, as you can see, as we move from the first step to the second, this direction is big, and we kind of carry that momentum, and we carry it a bit. We kind of do a bit of overkill here, actually, and we take the next step of the iterative process, and we estimate the third settings for the parameters to be a bit of an overshoot as to where the gradient descent has, in this case, correctly computed the computation. So there's a bit of overshooting here, and in fact, the overall performance will at least sometimes be a little bit worse when we're dealing with momentum. But very quickly, the momentum shoots you down into this hole, and it doesn't exactly get to the optimum right away, but it kind of circles the optimum much more quickly than does gradient-based machine learning using all of the data. So very quickly, there are some adaptive methods that take this velocity idea, this momentum idea, this idea of kind of continuing to go in directions that look promising. And instead of having it set to be one particular value, Obviously, this might be an overly simplistic approach because the overall curvature of the objective function's surface that you're trying to optimize will change depending on the data and the different settings of your weights, your parameters. So instead, you want to adapt to the nature of the learning process and the nature of the data. So very quickly, there's various methods you can apply here that use kind of per parameter learning rates that adjust our hyperparameters based on the actual parameters and not just some held out validation data. Grad from 2011 accumulates squared gradients and shrinks the step size for more frequent updated parameters. RMS prop from Thielman and Hinton a year later is a form of grad with exponential moving averages. And then Adam, so you're not going to need to know this. Spoiler alert for those in this course, I'm not likely to ask you to define grad and RMS prop because this is a bit of a stretch. I'm not going to ask you to read these papers either. But for those who want to go deeper, these are sort of the directions in which you'd want to learn. Some details about alternatives for adaptive methods to adjusting learning rates and hyperparameters. But I also wanted to highlight Adam. So Adam has a ton of problems with it as well, but this Kingma and Ba paper from 2015 it just exploded in terms of its popularity, in terms of its approach to optimization. It's roughly RMS prop with momentum and with bias corrected first and second moment estimates. We're not really going to get into first and second moments in this class, unfortunately, but essentially what it has here is these updates. This is a bit of a stretch again, so I should have the magnifying glass or the microscope here. These are equations I'm not going to ask you to learn, but it adjusts the weights at every iteration because we're still optimizing things. It does so with a learning parameter eta and with the this hyperparameter m hat and v hat, which we can obtain using these formulas here. V hat is very similar to, V hat is a function of v sub t, which is essentially a function of our velocity vector, like we saw before. I think we're going into too much detail here. This is just for curiosity. Find this paper, learn about it. It's extremely popular, and when you do machine learning, you're likely to use Adam under the hood, whether or not you know it. So these kinds of adaptive methods are very popular in deep learning, and usually it'll just work. You can set your default hyperparameters initially, and it'll adapt them to the data in a way that usually seems to give you good performance on training. But again, there are some problems with it, which we might talk about later. Convergence theory is a little bit subtle, and this paper describes it in a bit more detail. Some of the subtlety shows one of the problems of Adam, which it can fail to converge on some simple convex problems, but they propose a fix, and this again might be a bit beyond the scope of this introductory class, but I wanted to include it here just because of its importance in more advanced machine learning. So our anti-example is this. If you have a learning rate that's too large, again, you might bounce around or diverge. We talked about this earlier. Your parameters can end up shooting off to huge magnitudes. Even if you have regularization, like these learning rates can result in wildly fluctuating settings. So training accuracy can be erratic, and the net result of this is that validation loss will not stabilize. If you have too small of a learning rate, your loss can decrease very slowly. Your training may appear stuck. You may even make mistakes or slow progress. Pardon me. Excellent. So the diagnosis tool basically is always to plot your training curves, plot your validation curves over iterations of your learning. Ideally, these losses should converge, and it should be very clear that even with some noise, there'll be some convergence. We're going to see an example of this in a second. But if they don't, if the loss stays the same over all of your iterations, even with Adam or mini-batch stochastic gradient descent turned on, this can be a problem. Maybe you want to change your initial learning rate eta. If things are flat or slow and nothing seems to be learning, maybe you can try larger values of eta, or you can increase your momentum, and so on. So here's the key of it, examples. We're going to fit a very simple line. So our model family is going to be linear regression with two parameters, w sub 0 and w sub 1, which makes predictions on y. And we're going to explicitly use gradient descent and compare it to a closed form solution. So here's our code. We have synthetic data, which is produced through this linear regression. There's going to be some randomly added noise to it. And the noise is computed here. So stuff we've seen several times already. And here's just our training data. So we have a tiny amount of training data, x's and y's. So this is where we define our MSE loss. So our MSE loss is just the dot product of x and our weights. And the MSE loss is going to be the average of the squared difference between our predictions and the true value. The gradient of the MSE with regards to w. We've computed this in math before, but so we know how to compute these derivatives. MSE grad is just the derivative of our loss function given the training data and our particular value w, a particular setting of our parameters w. We set our learning rate to be 0.05. We're going to iterate for 200 iterations of training, and we're just going to basically go in the direction of our omegas. So essentially what we're doing now is the exact mathematical setup we saw earlier. Before we got into any mini batch stuff, just doing weights minus eta times the gradient. That's all we're implementing here. So for each of our iterations of machine learning, we're going to see our loss history, so how well we're doing according to our various settings as we change our settings w over time. We compute our loss. We append that loss to our loss history. Hopefully this loss will go down over time. We compute our gradient, given our data for all of our data, all of our training data. We multiply the gradient by eta. We subtract all of that from our settings of w, and we get a new settings of w. That goes from w sub t to w sub t plus 1. So we have new settings, and we iterate over and over again 200 times. And that's basically it. At the end of it, we're going to end up with a final optimized set of parameters w, and we'll have our loss history. If we just look at the last element of this list, using index -1, this will be the final loss at the end of training. And the net result is here. This array is our setting for w sub 0 and w sub 1, are the two parameters we can control. And our final loss after training on the training data is about 0.62. Okay, so far so good. So let's take a look at what actually happened. Here's the iterations over training. MSE loss initially started quite high. It started somewhere close to 14. But doing the simple updating of simply computing the gradient and then moving in the direction of the gradient according to the learning rate eta, very quickly dropped the MSE loss to something very small. And then it kind of I guess saturated might be the right word. Maybe it's the wrong word, but it got to a plateau where iterating more and more and more didn't seem to improve the MSE loss any further. We could have stopped at iteration 25, and that would have been probably enough for our purposes. Here is just a visualization of our data. Here's in blue circles are all the training data we have. The true line that generated these data is this orange dashed line, and then the gradient descent fit, which we obtained, is the blue line, which as you can see is very similar to the true data we're trying to predict. So we used a single learning rate, eta, and a fixed number of iterations. I think that was 200 if I remember correctly. Regardless, we know that we could have stopped after 25. I want you again to go into the code and run it yourself and change anything you can change. In this case, it's mostly going to be eta, so make eta very massive and see if the loss diverges. So if you're no longer going to get this nice curve where things improve and then stay good. If you make eta very big, what happens? Try making it very small. Maybe try a couple of iterations of making eta smaller and smaller and smaller and see if this L-shaped curve ends up being more like a horizon shape or more in that direction anyway. If you want, you can change the dimensionality. So you can go back to the code and change the dimensionality from just 1 to something bigger. It's going to be harder to visualize in graphical form, but you can still plot loss over time and see what happens. See if like you can get a nice L-shaped curve like this with not just a single value x, but massive input vectors x of d with d dimensions. So yeah, that's the first example. Here's the second. Here's logistic regression with mini-batch SGD. So before we were doing good old-fashioned regression, linearly in fact, and now we're going to do logistic regression and classification. So we're going to implement a simple mini-batch SGD optimizer for logistic regression. Here we're making a classification task. We've seen this function before. It comes from sklearn. So we're going to have 800 samples, 4 features, 3 of which are informative. None are going to be purely redundant. Then we're going to have a random seed. We're going to add a bias column. We're going to get it after we generate this data. We're going to get a train test split. Here the test size is 30% of the data, and so far nothing special. We're just generating a classification experiment, and we have 560 training samples. Each of them have 5 dimensions. I guess yeah, 4 of them are inputs, and 1 of them is the class. And then here we have the test case. We have 240 test data points, and we have 5 variables, 4 of which are our features, 1 of which is our class that we're trying to predict. So here, so in logistic regression, again, we use a sigmoid. A sigmoid has this shape. It's 1 divided by 1 plus the exponential of minus z, which is our input. Sometimes you can make these a bit more complicated, but we're going to keep it simple for now. Our logistic loss and gradient, I think I might leave this as an exercise for you to go through to try to remember how this works, but we saw the previous module on logistic regression. Actually, I spoke to one of you in class recently about why we're using sigmoids and not other functions. One of the advantages of using sigmoids is that the derivative of a sigmoid takes a standard form. Regardless, here is our loss. Our loss is y times, we talked about this in a previous module, so I'm not going to get back into it today, but it's like the value of y times the probability that you're predicting the positive case, plus 1 minus y times the probability that you're predicting the negative case. This gives you an overall loss about your performance. Again, we've done this already. I don't want to dig into it too much. Here is our gradient function, and here we're returning our loss and our gradient. Here we're defining the stochastic gradient descent, assuming the logistic function. We have our hyperparameters, eta, our batch size, the number of epochs we're going to run, and so on. And I leave this to you as an exercise to make sure that you understand how this is implementing the stochastic gradient descent from a few moments ago. But just to highlight it, we're going to be doing several epochs of training, and in each epoch, we're going to have a different batch. That batch will have a different batch size. We're going to use different indices. These indices basically will mean we're going to run through these different batches, from the start to the size of the batch size. So we're not going to look at all the data. We're only going to use some of the data, and at every iteration, we're going to use a different sample of the data for our updates. We get our x's and y's from those batches. We compute the loss and the gradient on that batch. We multiply the gradient by our learning rate, subtract that from our weights. This gives us our new weights, which are then going to be used in our next batch, and then in our next epoch, and so on. And this is going to give us an overall history of all of our losses. So again, just like we saw before, we're going to append losses at every step to our history. Here's where we define our SGD logistic function with our parameters, our training data, our learning rate, our batch size, number of epochs, and so on. When you run this, just like we talked about a moment ago with worked example 1, go ahead and change eta to something very large, change it to something very small, and see if what I'm about to show you changes drastically. But you can look at the same sort of analysis like we saw with good old-fashioned regression. We have our length of the history. We have our final SGD at the end of training. Here it is. So our history is going to be stored in loss_hist for history of the SGD approach to learning. So actually, sorry, the first 5. So it's not the last one anymore. This is taking the first 5. So initially the loss was 0.69, and then we went to 0.68, and then we went to 0.67, and then up to 0.68, and then down to 0.67 again. So there seems to be a downward trend in our losses, at least for our first few iterations of this algorithm, but there also seems to be some backsliding to somewhat higher losses, which we normally don't like, but maybe in the big picture things will be okay. And in big picture, things generally seem to be kind of okay. Here is our history. Basically, it's plotting what we stored before in our loss history. SGD is going to be plotted using, code like very similar to the ones we saw earlier. Over time, over all of these updates, generally the loss of these mini batches is improving, but because of the randomness of sampling, sometimes the loss of these samples can get very large, like you see in some of these spikes. This is going to look very similar to what you would see if you were to use like an off-the-shelf machine learning algorithm on some massive neural network, for example. Again, even though we're doing simple logistic regression with a simple synthetic data set, you're going to see in practice data that looks a lot like this, which is why I wanted to show you a more realistic example than kind of cartoon examples you see in a lot of other classes. This fluctuation can be unnerving, and it can lead to a little bit of concern. Normally, you might have a couple of different losses from a couple of different architectures or machine learning algorithms. One of them might be a lot higher or lower than the other, indicating the superiority or inferiority of that model, respectively. But there's a lot you can see here. As a general downwards trend, it tends to saturate very quickly and not get much better after what looks like about 100 iterations. And there is an awful lot of noise in this curve, right? So the wild fluctuations, at least visually, seem to be pretty large. It's hard to tell whether a loss of 0.8 and 0.3, that difference, if it's large or not, that depends on all kinds of other factors, but it is a bit messier than we'd like to see, and maybe this is fine. We'd want to go ahead and evaluate on validation sets in terms of actual classification, error on validation sets, but this is realistic. This loss seems noisy. It's largely noisy because we're doing mini batching, and we have a point here for every mini batch. And some matches will give you, crazily different performance because there happen to be samples of very difficult data. But generally, the trend should be downwards, always, regardless of whether you're doing it with SGD or without. The trend should be downwards. You should go ahead and try eta and different batch size values. So it's going to be very easy for you to download the code and run it and see if you can get anything better than this. I'm sure it's always possible to do worse. I'm sure you can get something that fluctuates much more wildly than this. But see if you can get a curve that still has a downward trend, but over time the fluctuations become flattened, if that's even possible. You can try breaking things. Try setting eta and batch size so that convergence never seems to happen at all. Look not only to the overall trends and the overall amount of fluctuation, but look also to the speed with which you're converging. So how quickly do you seem to get to the average being more or less stable? Here the average, you see here, seems to be stable at around 0.5 as early as 100 iterations. How quickly do you get there is something to also look into when you're doing your little experiments. When using this gradient-based approximation, when taking these derivatives, you should monitor training loss versus iteration. So look at divergence, plateaus, oscillations. We've talked about this. Consider validation loss and iteration. So we're looking at our loss on training data, but you can also simultaneously look at loss on held out validation that's nevertheless not your test set just yet. So, when you're minimizing the curve of your training loss, generally validation loss should also go down, subject to various fluctuations also. But if the overall trend seems to be going up again, then you seem to have hit and passed a optimum point for your settings, the optimum number of iterations. So consider stopping at that point. You can then also go back into your bag of tricks, try better regularization, tune your hyperparameters, and use your validation set to get to an optimum sweet spot. Try simple metrics like accuracy, mean squared error on training and validation, and ensure that optimization is improving, that you're not just fitting noise. You should also check other metrics. So usually, like, people just kind of devolve into thinking about accuracy and mean squared error, but you can also look at other metrics like false positive rates, precision recall, and so on. If optimization is very slow, so if this curve over here seems not to trend downwards even as quickly as this, but seems to be very flat, even if it's somewhat downward, it's still very flat, this can mean that optimization is taking too long. You need to potentially consider changing learning rate, changing the batching size, or using an adaptive method or one based on momentum to leap towards the solution as quickly as possible. And if you do these kinds of checks and you continuously throw a wide range of tools at the problem, generally you'll perform well. So to do that, you have to remember concepts of evaluation, concepts of cross-validation, concepts of bias versus variance, concepts of regularization. We're starting to accumulate a set of tools now that we can apply to this problem so that when we're staring at curves like this one late at night or close to a deadline, we will still have approaches we can take in order to try to improve the learning process. Again, there's ethics and risks that come into play here. Although optimization seems to be, it's a very technical problem, like we have all of these different ways that we can minimize error or minimize our objective function, all the same old risks still apply. The same old kind of failures still exist. So, training can diverge or get stuck, but only looking at the metrics mean that we still might be deploying something that isn't actually optimized well or might not generalize well or may have been trained in empirical situations which have shortcuts and cheats like the leakage of information from a test set to a training set can make it look like the training data process is highly performant, but it's incorrect. It's cheating. For reproducibility, SGD uses the concept of randomness in shuffling and initialization. This is very helpful. This is very similar to the concept of boosting that we see in very basic data science and statistics. So the more you can use simulation or random sampling to give you lots of different estimates and then combining them or conflating them into overall statistics, like averages of averages, is a good thing. You're going to have you're going to be able to express your performance in terms of ranges of confidence and intervals. You'll be able to see overall trends that might exist within the presence of lots of observed noise, but at least the observed noise is now explicit. So now you can think a little bit about confidence. Again, you might look at something like this and be less confident in the overall performance than you might with a curve that looks like this one. But that's part of the overall process, becoming comfortable with uncertainty. Without fixing seeds, like we've done a lot in all the examples I gave you, or documenting hyperparameters or how they're tuned, the results will be hard to produce. This is a bit of a separate thing than what I was just talking about a moment ago, but both are true. It's true that sometimes doing lots of random samples is a good way of understanding the overall performance, because the average of all those overall random samples will give you an overall good understanding of performance on average. So totally random sampling is good from that perspective. But from the perspective of engineering and reproducibility, we want to kind of minimize total randomness. We might still use SGD, and we might still use batching, and we might still do like a apparently random procedure to take care of things like mini batches and optimization, like in this module, or the randomness in cross-validation. But as long as that cross-validation and randomness of mini batching is reproducible, we're fine. We don't want to have a situation where we deploy some code or make it open source or report our results in research papers, and we put our code online, but we don't tell everybody what our random seed was. maybe the random seed we used was a very, very magical one that gave us the great performance that we're reporting. But for the billions of other possible random seeds people could have started with, the performance is way off than what we're reporting, right? Most of the time, that might be just a simple problem that is, a problem of miscommunication. We should have told people what a random seed was and we didn't, and that's on us for not being totally transparent. Still a problem, but it can also give the impression that the results you got are not trustworthy, which is more of a problem. So it's always a good idea to document as much as you can at all points in the process. Again, in practice, I kind of jumped over Atom just because of its relative complexity relative to the nature of this course. But you can think of Atom more or less as an adaptive way to adjust hyperparameters within the context of momentum when we're trying to do SGD with mini batches. So hopefully you understand where it is generally. You don't have to implement it, and I'm not going to be mean about it and ask you lots of questions about it. But you're going to see it in practice. You're certainly going to see Atom when we get to neural networks. So Atom fits in into this overall training objective. We're still going to change our parameters W at iteration t to iteration t+1, and we're going to do so based on learning rates eta and on some function of the derivatives of our objective function with regards to our parameters. Atom is going to update other hyperish parameters, M and V, which is sort of within this overall conception. We have the actual formula several slides ago. In practice, all of this will mostly be hidden from you. It's fine, I think, to use Atom just as a function that you happen to call, but it can also be a little bit helpful to understand at least the context in which it's being run. So if you're using Atom because you're supposed to, fine. If the performance you're getting is a bit wild, like if the problems of momentum-based learning seem to be exhibited within what you're observing when you're looking at those loss curves, then this might hopefully trigger in you, at the very least, the idea that this could be a fault of using the Atom optimizer. I just wanted to show you a couple of things here. This is all high level. This is not going to run if you just copy and paste this code. But we have like a model that we built, some neural network stored in a model. We're going to have some cross entropy loss. This could be a MSE loss. It could be a classification loss. Whatever the loss is, we have some criterion. It doesn't really matter. We can use Atom for regression, for classification, for generative-based prediction with cross entropy. In all of those cases, we would use, like in one case, we could use SGD with something like momentum. And in this case, momentum would have a fixed parameter, like 0.9. We could try to optimize it on validation data, but we'd get some optimized set of parameters. Similarly, Atom would have a similar setup. We'd still say use torch.optimatom, which is valid code, just like torch.optim.sgd is valid code that you yourself would use. You still pass the parameters in, you still pass the learning rate, which you could still optimize. You still pass a weight decay, which we haven't really talked about yet. But you'll see there's no momentum because momentum is something that is handled under the hood in this Atom function. So all of this complicated stuff that I glossed over very quickly before with M17 and V17, this is handled for you automatically when you actually run Atom in the real world. So for most of you, you can set it and forget it. Anyway, apart from that, everything else is generally the same. You have an optimizer. We can set it to be our Atom optimizer, or we can set it to be our SGD optimizer, and we can go off to the races. Normally, you're not going to write your update functions by hand. This will be handled for you automatically by torch.optim for optimizer. We'll just choose whether we're using SGD or Atom, and that's it. So this is both good and bad. This is good from the point of view that you can do Atom optimization right away without having to know anything about it. You can learn a little bit about torch.optim at this link down here. It's a bit of a problem, though, because if you don't know how things work under the hood, then when things break, then you don't really know where to go for potential solutions. We're not going to talk, we didn't talk in any depth about how Atom works, really, but at the very least, by now you know a little bit about how momentum-based learning can fail. And so if you're doing real projects, you might at least know that you can use SGD or you can use Atom. You can know that you can adjust the learning rates through some hyperparameter optimization process. And ideally, you can solve problems of the type we kind of visited a few moments ago that way. So a bit of a broader connection for those of you who are curious. Modern deep learning will involve at least hundreds of millions of parameters, often hundreds of billions of parameters. But those updates on these neural networks will use either SGD or ADAM or some complicated variant of either of these. So the research questions you might see if you were to go into research projects in fourth year or certainly grad school might have to do with how does SGD generalize to very over-parameterized regimes where your capacity is very massive. If there's implicit regularization, like we talked about a few slides ago, does good old-fashioned gradient descent provide some benefits to it? And what kind of different optimizers affect questions of robustness and fairness? This is, for what it's worth, kind of the question that my lab asks a lot. We care about robustness, we often care about fairness, and we're kind of tuning optimizers. Like some of my students in our lab are literally making modifications to special variants of ADAM in order to take the advantages of ADAM and make sure that they're robust and fair approaches. This module is really superficial, like I mentioned at the very beginning. These are just foundational tools to think about these questions. We introduced the idea of using gradients to kind of go downwards in these bowls, these curved objective functions. So the derivatives kind of tell you the direction to move in and the amount to move in those directions. And this generalizes from one-dimensional data to multi-dimensional data. It generalizes from having one parameter to optimize or two to hundreds of millions. So, surface level, hopefully you get an idea. I think the main thing to take away from here is the concept of mini-batching and the concept of doing stochastic gradient descent using, instead of all of the data at once when you're computing your objective functions and the derivatives on the objective functions, using only subsamples of them. That was kind of the key thing we mentioned today, so please make sure you understand that. And you can check if you understand that by doing these quick checks on the slides that are available online. Here are the references. These are some very fundamental papers here, in particular this Tillman and Hinton paper from 2012 and this Kingma et Ba paper from 2015. So if you're feeling ambitious, I highly recommend you read these, as these are foundational to our discipline. Again, thanks so much. See you next time.